Chapter 6 Geometers Future Shock. In his famous book Future Shock, author Alvin Toffler defined the term in the title as the shattering stress and disorientation that we induce in individuals by subjecting them to too much change in too short a time. In the 19th century, mathematicians, scientists, and philosophers experienced precisely such a shock. In fact, the millennia-old belief that mathematics offered the external and immutable truths was cast. This unexpected intellectual upheaval was caused by the emergence of new types of geometries known as non-Euclidean geometries. Even though more non-specialists may have never even heard of non-Euclidean geometries, the magnitude of their revolution in thought introduced by these new branches of mathematics has been likened by some to the inaugurated by the Darwinian theory of evolution. To fully appreciate the nature of this sweeping change in worldview, we have first to briefly probe the historical mathematical backdrop. Euclidean Euclidean truth. Until the beginning of the 19th century, it is if there was one branch of knowledge that had been regarded as the apotheosis of truth and certainty, it was Euclidean geometry, the traditional geometry we learned in school. Not surprisingly, therefore, the great Dutch Jewish philosopher Baruch Spinoza 1630 to 77 entitled his book attempt to unify science, religion, ethics, and reason, ethics demonstrated in geometrical order. Moreover, in spite of the clear distinction between the ideal, Platonic world of mathematical forms and physical reality, most scientists regard the objects of Euclidean geometry simply as the distant abstractions of the real physical counterparts. Even staunch empiricists such as David Hume, 1711 to 76, who insisted that the very foundations of science were far less certain than anyone had ever suspected, concluded that Euclidean geometry was as solid as the Rock of Gibraltar. In an inquiry concerning human understanding, Hume identifies truths of two types. All the objects of human research or inquiry may naturally be divided into two kinds, to wit, relations of ideas and matters of facts. Of the first kind are every affirmation which is either intuitively or demonstratively certain. Propositions of this kind are discoverable by the mere operation of thought, without dependence on what is anywhere existent in the universe. Though there never a circle or a triangle in nature, the truths demonstrated by Euclidean would or forever retain their certainty and evidence. Matters of fact are not ascertained in the same manner, nor is our evidence of the truth, however great or alike nature with the foregoing. The contrary of every matter of fact is still possible, because it can never imply a contradiction. That the sun will not rise tomorrow is no less intelligible a proposition, and implies no more contradiction than the affirmation that is that it will rise. We should in vain therefore attempt to demonstrate its falsehood. In other words, while Hume, like all empiricists, maintained that all knowledge stems from observation, geometry and its truths continue to enjoy a privileged status. The preeminent German philosopher Immanuel Kant, 1724 to 1804, did not always agree with Hume, but he also exalted Euclidean geometry to a status of absolute certainty and unquestionable validity. In his memorable critique of progression, Kant attempted to reverse in some sense the relationship between the mind and the physical world. Instead of impressions of physical reality being imprinted on an otherwise entirely passive mind, Kant gave the mind the active function of constructing or processing the perceived universe. Turning his attention inward, Kant asked not what we can know, but how we can know what we can know. He explained that while our eyes detect particles of light, these do not form an image in our awareness until the information is processed and organized by our hands. A key role in this construction process was assigned to the human intuitive or scientific a priori grasp of space, which in turn was taken to be based on Euclidean geometry. Kant believed that Euclidean geometry provided the only true path for processing and conceptualizing space, and that its intuitive universal acquaintance with space was at the heart of our experience of the natural world. In Kant's words, space is not an empirical concept which has been derived from an external experience. Space is a necessary representation a priori, forming the very foundation of all external intuitions. On this necessity of an a priori representation of space rests the apodictic certainty of all geometrical principles and all the possibilities of the constructions a priori. For if the intuition of space were a concept gained a posteriori, borrowed from general external experience, the first principles of mathematical definition would be nothing but perceptions. They would be exposed to all the accidents of perception, and there being but one straight line between 2 points would not be a necessity, but only something taught in each case by experience. To put it simply, according to Kant, if we perceive an object, then necessarily the object is spatial and Euclidean. Hume's and Kant's ideas bring to the forefront the two rather different but equally important aspects that had been historically associated with Euclidean geometry. The first was the state that Euclidean geometry represents the only accurate description of physical space. The second was the identification of Euclidean geometry with the form, decisive, and infallible deduction structure. Taken together, these two presumed properties provided mathematicians, scientists, and philosophers with what they regarded as their strongest evidence that informative, inescapable truths about the universe to exist. Until the 19th century, these statements were taken for granted, but were they actually true? The foundations of Euclidean geometry were laid around 300 BC by the Greek mathematician Euclid of Alexandria in a monumental 13-volume opus entitled The Elements. Euclid attempted to erect geometry on a well-defined logical base. He started with 10 axioms assumed to be indisputably true and sought to prove a large number of propositions on the basis of those postulates by noting other than logical deductions. The first four Euclidean axioms were extremely simple and exquisitely concise. For instance, the first axiom read, between any 2 points a straight line may be drawn. The fourth one stated all right angles are equal. By contrast, the fifth axiom, known as the parallel postulate, was more complicated in its formulation and considerably less self-evident. If two lines lying in a plane intersect a third line in such a way that the sum of the internal angles on one side is less than two right angles, then two lines inevitably will intersect each other if extended sufficiently on that side. Figure 39 demonstrates physically the contents of this axiom. While no one adopted the truth of this statement, it lacked the compelling simplicity of the other axioms. All indications are that even Euclid himself was not entirely happy with his swift postulate. The proofs of the first 28 propositions in the Elements do not make use of it. The equivalent version of the fifth, most cited today, appeared first in commentaries by the Greek mathematician Proclus in the 5th century, but it is generally known as the Playfair axiom, after the Scottish mathematician John Playfair, 1748 until 1815. It states, given a line and a point not on the line, It is possible to draw exactly one parallel line to given line through the point figure 40. The two perfections of the axiom are equivalent in the sense that platform axiom together with the other axioms necessarily implies Euclid's original fifth axiom and vice versa. Over the centuries, the increasing discontent with the fifth axiom resulted in a number of unsuccessful attempts to actually prove it from the other nine axioms or to replace it by a one more obvious postulate. When those efforts failed, other geometers began trying to answer an intriguing what if question. What if the fifth axiom did in fact not prove true? Some of those endeavors started to raise nagging doubts of whether Euclid's axioms were truly self-evident rather than being based on experience. The final, surprising verdict eventually came in the 19th century. One could create new kinds of geometry by choosing an axiom different from Euclid's fifth. Furthermore, these non-Euclidean geometries could in principle describe physical space just as accurately as Euclidean geometry did. Let me pause here for a moment to allow for the meaning of the word chosen to sink in. For millennia, Euclidean geometry had been regarded as unique and inevitable, the sole true description of space. The fact that one could choose the axioms and obtain an equally valid description turned the entire concept on its ear. The certain carefully constructed deductive axioms suddenly become more simple to a game in which the axioms simply play the role of the rules. You could change the axioms and play a different game. The impact of this realization on the understanding of the nature of mathematics cannot be overemphasized. Quite a few mathematicians prepare the ground prepared the ground for the final assault on Euclidean geometry. Particularly notable among them were the Jesuit priest Girolamo Saccheri, 1667 until 1732, investigated the consequences of replacing the fifth postulate by a different statement, and the German mathematicians Georg Klugel, 1739 until 1812, and Johann Heinrich Lambert, 1728 until 1777, who were the first to realize the alternative geometries to the Euclidean could exist. Still, somebody had to put the last nail in the coffin of the idea of a geometry being the one and only representation of space. That honor was shared by three mathematicians, one from Russia, one from Hungary, and one from Germany. New words. The first to publish an entire treatise on a new type of geometry, one that could be constructed on a surface shape like a curved saddle, figure 41a, was the Russian Nikolai Ivanovich Lobachevsky, 1792 until 1846, figure 42. In this kind of geometry, now known as hyperbolic geometry, Euclid's five postulate is replaced by the statement that given a line and a plane and a point not in this line, there are at least two lines through the point parallel to the given line. Another important difference between Lobachevskian geometry and Euclidean geometry is that while in the latter the angles in triangle always add up to 180 degrees, figure 41b. In the former, the sum is always less than 180 degrees. Because Lobachevsky's work appeared in the rather obscure Kazan Bulletin, it went almost entirely unnoticed until French and German translations started to appear in the late 1830s. Unaware to Lobachevsky's work, a young Hungarian mathematician, János Bolyai, 1802 until 60, formulated a similar geometry during the 1820s. Bursting with youthful enthusiasm, he wrote in 1823 to his father, the mathematician Varkas Bolyai, figure 43. I have found things so magnificent that I was astounded. I have created a different new world out of nothing. By 1825, János was already able to present to the elder Bolyai the first draft of his new geometry. The manuscript was entitled The Science Absolute of Space. In spite of the young man's exuberance, the father was entirely convinced of the soundness of Janos' ideas. Nevertheless, he decided to publish the new geometry as an appendix to his own two-volume treatise on the foundations of geometry, algebra, and analysis, the supposedly inviting title of which read Essay on the Elements of Mathematicians for Studious Youths. A copy of the book was sent in June 1831 to Farkas' friend Carl Friedrich Gauss, 1777 until 1855, figure 44, who was not only the most prominent mathematician of the time, but who is considered by many, alongside with Archimedes and Newton, to be one of the three greatest of all time. The book was somehow lost in the chaos created by a cholera epidemic, and Farkas had to send a second copy. Gauss sent out a reply on March 6, 1832, and his comments were not exactly what the young Janus expected. If I commence by saying that I am unable to praise the work, you would certainly be surprised for a moment, but I cannot say otherwise. To praise it would be to praise myself. Indeed, the whole contents of the work, the path taken by your son, the results to which he is led, coincide almost entirely with my meditations, which have occupied my mind partly for the last 30 or 35 years. So I remain quite stupefied so far as my own work is concerned, of which up till now I have put little on paper. On my intention must not let was not to let it be published during my lifetime. Let me parenthetically note that apparently Gauss felt the radically new geometry would be regarded by the Kantian philosophers, to whom he referred as the Boethians, synonymous with stupid for the ancient Greeks, as philosophical heresy. Then Gauss then continued, on the other hand, it was my idea to write down all these letters so that at least it should not perish with me. It is therefore a pleasant surprise that with me that I am spared this trouble, and I am very glad that it is the son of my old friend who takes the precedence of me in such a remarkable manner, while Farkas was quite pleased with Gauss' praise, while he looked which he took to be very fine. Janos was solely devastated. For almost a decade he refused to believe what that Gauss claimed to priority what was not false, and his relationship with his father, whom he suspected of prematurely communicating the results to Gauss, was seriously strained. When he finally realized that Gauss had actually started working on the problem as early as 1799, Janos became deeply embittered, and his subsequent mathematical work, he left some 20,000 pages of manuscript when he died, became rather lackluster by comparison. There is very little doubt, however, that Gauss had indeed given considerable thought to non-Euclidean geometry. In a diary entry from September 1799, he wrote, in principis geometriae egregios progressus fecimus. About the principle of geometry, we obtained wonderful achievements. Then in 1813 he noted, in the theory of parallel lines, we are no further than Euclid was. This is the patie honteuse, shameful part of mathematics, which sooner or later must get a very different form. A few years later, in a letter written on April 28, 1817, he stated, I am coming more and more to the conviction that the necessity of our Euclidean geometry cannot be proved. Finally, and contrary to Kant's views, Gauss concluded that Euclidean geometry could not be viewed as a universal truth, and that rather one would have to rank Euclidean geometry not with arithmetic, which sense a priori, but approximately with mechanics. Similarly, conclusions were reached independently by Ferdinand Schweikart, 1780 until 1859, a professor of jurisprudence, and the later informed Gauss of his work sometime in 1818 or 1819. Since neither Gauss nor Schweikart actually published his results, however, the priority of first publication is traditionally credited to both Lobachevsky and Bolyai, even though the two can hardly be regarded as the sole creators of non-Euclidean geometry. Hyperbolic geometry broke on the world of mathematics like a thunderbolt, dealing a tremendous blow to the perception of Euclidean geometry as the only infallible description of space. Prior to the Gauss-Lobachevsky-Bolyai work, Euclidean geometry was in effect the natural world. The fact that one could select a different set of axioms and construct a different type of geometry raised for the first time the suspicion that mathematics is, after all, a human invention, rather than a discovery of truths that exist independently of the human mind. At the same time, the collapse of the immediate connection between Euclidean geometry and true physical space exposed what appeared to be fatal deficiencies in the idea of mathematics as the language of the universe. Euclidean geometry's privileged status went from bad to worse when one of Gauss' students, Bernhard Riemann, showed that hyperbolic geometry was not the only non-Euclidean geometry possible. In a brilliant lecture delivered in Göttingen on June 10, 1854, Figure 55 shows that the first page of the published lecture, Riemann presented his views on the hypothesis that lay at the foundation of geometry. He started by saying that geometry presupposes this concept of space, as well as assuming the basic principles for constructions in space. It gives only nominal definitions of these things, while their essential specifications appear in the form of axioms. However, he noted, the relationship between these presuppositions is left in the dark. We do not see whether or to what extent any connection between them is necessary, or a priori whether any connection between them is even possible. Among the possible geometry theories, Riemann discussed elliptic geometry of the type that one would encounter on the surface of space, Figure 41c. Note that in such a geometry, the shortest distance between 2 points is not the straight line, it is rather a segment of a great circle whose center coincides with the center of the sphere. Airlines take advantage of this fact. Flights from the United States to Europe do not follow what would appear as a straight line on the map, but rather a great circle that initially bears northward. You can easily check that any great circles meet at two diametrically opposite points. For instance, two meridians on Earth which appear to parallel at the equator meet at two poles. Consequently, unlike in Euclidean geometry, where there is exactly one parallel line to an external point, and hyperbolic geometry, in which there are at least two parallels, there are no parallel lines at all in the elliptic geometry on a sphere. Riemann took the non-Euclidean concepts one step further and introduced geometries in curved space in 3, 4, and even more dimensions. One of the key concepts expanded upon by Riemann was that of the curvature, the rate at which a curve or a surface curves on the surface curves. For instance, the surface of an axle curves more gently around its girth than along a curve passing through one of its point edges. Riemann proceeded to give a precise mathematical definition of curvature in space of any number of dimensions. In doing so, he solidified the marriage between algebra and geometry that had been initiated by Descartes. In Riemann's work, equations in any number of variables found their geometrical counterparts, and the concept from the advanced geometries became partners of equations. Euclidean geometry's eminence was not the only victim of the new horizons that the 19th century opened for geometry. Kant's ideas of space did not survive much longer. Recall that Kant asserted that information from the senses is organized exclusively along Euclidean templates before it is recorded in our consciousness. Geometers of 19th century quickly developed intuition in the non-Euclidean geometries and learned to precise the world along those lines. The Euclidean perception of space turned out to be learned after all, rather than intuitive. After all of these dramatic developments led the great French mathematician Henri Poincaré, 1854 until 1912, to conclude that the axioms of geometry are neither a priori intuitions nor experimental facts. There are conventions, emphasis added, our choice among all possible conventions is guided by experimental facts, but it remains free. In other words, Poincaré regarded axioms only as definitions in disguise. Poincaré's views were inspired not just by the non-Euclidean geometries described so far, but also the proliferation of other new geometries, which before the end of the 19th century seemed to be almost getting out of hand. In projective geometry, such as that obtained when an image on celluloid film is projected is projected is projected onto a screen. For instance, one could literally interchange the roles of points and lines, so that theorems about points and lines in this order became theorems about lines and points. In differential geometry, mathematicians use calculus to study local geometrical properties of various mathematical species, such as the surface of a sphere of a torus. This and other geometries appeared at first blush at least to be ingenious inventions of imaginative mathematical minds rather than accurate descriptions of physical space. How then could one still defend the concept of God as a mathematician? After all, if God ever geometrized, a phrase attributed to Plato by historian Plutarch, which of these many geometries grows the divine practice? The rapidly deepening recognition of the shortcomings of the classical Euclidean geometry forced mathematicians to take a serious look at the foundations of mathematics in general and at the relationship between mathematics and logic in particular. We shall return to this important topic in chapter 7. Here, let me only note that the very notion of the self-evidence of axioms had been shattered. Consequently, while the 19th century witnessed other significant developments in algebra and analysis, the revolution in geometry probably had the most influential effects on the views of the nature of mathematics, on space, numbers, and humans. Before mathematicians could turn to the overarching topic of the foundations of mathematics, however, a few smaller issues require immediate attention. First, the fact that non-Euclidean geometries had been formulated and published did not necessarily mean that these were legitimate offspring of mathematics. There was the ever-present fear of inconsistency, the possibility that carrying these geometries to the ultimate logical consequences will produce unresolvable contradictions. By the 1870s, the Italian Eugenio Beltrami 1835 until 1900 and the German Felix Klein 1849 until 1925 had demonstrated that as long as Euclidean geometry was consistent, so were non-Euclidean geometries. This still left open the bigger question of the solidity of the foundations of Euclidean geometry. Then, there was the important matter of relevance. Most mathematicians regarded the new geometries as amusing curiosities at best, while Euclidean geometry derived much of its historical power from being seen as the description of real space. The non-Euclidean geometries had been perceived initially as not having any connection whatsoever to physical reality. Consequently, the non-Euclidean geometries were treated by many mathematicians as Euclidean geometries precursors. Henry Poincaré was a bit more accommodating than most, but even he insisted that if humans were to be transported to a world in which that accepted geometry was non-Euclidean, then it was still certain that we should not find it more convenient to make a change for Euclidean to non-Euclidean geometry. Two cases therefore loom large. Could geometry in particular and other branches of mathematics in general be established on solid axiomatic logical foundations? And two, what the relationship, if any, between mathematics and the physical world? Some mathematicians adopted a pragmatic approach with respect to the validation of the foundation of geometry, disappointed by the realization that what they regarded as absolute truths turned out to be more experience-based than rigorous. They turned to the arithmetics of numbers, the scarce analytic geometry, in which points in the plane were identified with ordered pair of numbers, cycles with pairs satisfying a certain equation, see chapter 4 and so on, provided just the necessary tools for the re-erection of the foundation of geometry on the basis of numbers. The German mathematician Jacob Jacobi, 1804 until 51, presumably expressed those shifting tides when he replaced Plato's God ever geometricized by his own motto, God ever arithmeticized. In some senses, however, this efforts only transported the problem to a different branch of mathematics. While the great German mathematician developed 1862 until 1943, they succeeded in demonstrating that Euclidean geometry was consistent. As long as arithmetic was consistent, the consistency of the data was far from ambiguously established at the point on the relationship between mathematics and the physical world. A new sentiment was in the air. For many centuries, the interpretation of mathematics as a reading of the cosmos had been dramatically and continuously enhanced. The mathematician of sciences by Galileo, Descartes, Newton, de Bernoulli, Pascal Lagrange, Quetelet, and others was taken as strong evidence for an underlying mathematical design in nature. One could clearly argue that if mathematics wasn't the language of the cosmos, why did it work as well as it did in explaining things, ranging from the basic laws of nature to human characteristics? To be sure, mathematicians did realize that mathematics dealt only with rather abstract Platonic forms, but those were regarded as reasonable idealizations of the actual physical elements. In fact, the feeling that the book of nature was written in the language of mathematics was so deeply rooted that many mathematicians absolutely refused even to consider mathematical concepts and structures that were not directly related to the physical world. This was the case, for instance, with the colorful Girolamo Cardano 1501 until 1776. Cardano was an accomplished mathematician, renowned physician, and compulsive gambler. In 1545, he published one of the most influential books in the history of algebra, the Ars Magna, the Great Act. This comprehensive treatise, Cardano, explored in great detail solutions to algebraic equations from the simple quadratic equation in which the unknown appears to the second power x squared to the pioneering solutions to cubic involving x cubed and quadratic involving x squared to the x equations. In classical mathematics, however, quantities were often interpreted as geometrical elements. For instance, the value of the of the unknown x was identified with a line segment of that length. The second power of x squared was an area, and the third power x cubed was a solid having the corresponding volume. Consequently, in the first chapter of the Ars Magna, Cardano explains, we conclude our detailed consideration with the cubic, others being merely mentioned, even if generally in passing. For as positio, the first power refers to a line, quadratum the square to a surface, and cubum the cube to a solid body. It would be very foolish for us to go beyond this limit. Nature does not permit it. Thus it will be seen all those methods up to and including the cubic are fully demonstrated, but the others which we will add either by necessity or out of curiosity, we do not go beyond barely setting out. In other words, Cardano argues that since the physical world was as perceived by our sense contains only three dimensions, it would be silly for mathematicians to concern themselves with a higher number of dimensions or with equations of a higher degree. A similar opinion was expressed by the English mathematician John Wallis 1660 until 1703, from whose work Arithmetica Infinitorum Newton learned methods of analysis. In another important book, Treatise of Algebra, Wallis first proclaimed nature inappropriate of speech does not admit more than three local dimensions. He then elaborated, a line drawn into a line shall make a place or surface. This drawn into a line shall make a solid. But if this solid be drawn into a line or this plane into a plane, what shall it be? What shall it make? A plano plane? This is a monster in nature, and even possible that in chimera, a fire-breathing monster in Greek mythology composed of a serpent, lion, and goat, or a centaur in Greek mythology, a being having the upper portion of a man and the body and the legs of a horse. For length, breadth, and thickness take up the whole of space. Nor can our fancy imagine how there should be four local dimensions beyond these three. Again, Wallis' logic here was clear. There was no point in even imagining a geometry that did not describe real space. Opinions eventually started to change. Mathematicians of the 18th century were the first to consider time as a potential fourth dimension. In an article entitled Dimension, published in 1754, the physicist Jean d'Alembert, 1717 wrote until 83, wrote, I stated above that it is possible to conceive of more than three dimensions. A man of parts of my acquaintance hold that one may, however, look upon duration as a fourth dimension, and that the product of time, the solidity is in a way a product of four dimensions. This idea may be challenged, but it seems to me to have some merit other than that of mere novelty. The great mathematician Joseph Lagrange went even one step further, stating more assertive in 1797, since a portion of a point in space depends upon three rectangular coordinates, these coordinates in the problems of mechanics are conceived as being functions of t-time. Thus we may regard mechanics as a geometry of four dimensions, and mechanical analysis as an extension of geometric analysis. These both ideas open the door for extensions of mathematics that had previously been considered inconceivable, geometries in any number of dimensions, which totally ignore the question of whether they had any relation to physical space. And might have been wrong in believing that our senses of spatial perception follow exclusively Euclidean modes, but there is no question that our perception operates most naturally and intuitively in no more than 3 dimensions. We can relatively easily imagine how our three-dimensional world would look in Plato's two-dimensional universe of shadows, but going beyond 3 to a higher number of dimensions truly requires a mathematician's imagination. Some of the groundbreaking work is the treatment of n-dimensional geometry. Geometry in an arbitrary number of dimensions was carried by Hermann Günther Grassmann, 1809 until 77. Grassmann, one of 12 children, and himself the father of 11, was a school teacher who never had a university mathematical training. During his lifetime, he received more recognition for his work in linguistics, particularly for his studies of Sanskrit and Gothic, than for his achievements in mathematics. One of his biographers wrote, "It seems to be Grassmann's fate to be rediscovered from time to time, each time as if he had been virtually forgotten since his death." Yet Grassmann was responsible for the creation of an abstract science of spaces, inside which the usual geometry was only a special space. Grassmann published his pioneering ideas, originating a branch of mathematics known as linear algebra in 1844, in a book commonly known as the Ausdehnungslehre, meaning Theory of Extensions. The full title read Linear Extension Theory, a New Branch of Mathematics. In the foreword to the book, Grassmann wrote, "Geometry can in no way be viewed as a branch of mathematics. Instead, geometry relates to something already given in nature, namely space. I also had realized that there must be a branch of mathematics which leads in a purely abstract way, laws similar to those of geometry." This was a radically new view of the nature of mathematics. To Grassmann, the traditional geometry, the heritage of the ancient Greeks, deals with physical space and therefore cannot be taken as a true branch of abstract mathematics. Mathematics to him was rather an abstract construct of the human brain that does not necessarily have any application to the real world. It is fascinating to follow the seemingly trivial train of thought that set Grassmann on the road to his theory of geometry algebra. It started with the simple formula AB, BC, AC, which appears in any geometry book in the discussion of lengths of line segments, figure 46a. Here, however, Grassmann noticed something interesting. He discovered that this formula remains valid irrespective of the order of the points A, B, C, as long as one does not interpret A, B, B, C, and so on merely as lengths, but also assigns to them direction such that AB, BA, AB. For instance, if C lies between A and B, as in figure 46b, then AB, AC, CB, but since CB, BC, we find that AB, AC, BC, and the original formula AB, BC, AC is recovered simply by adding BC to both sides. This was quite interesting in itself, but Grassmann's extension contained even more surprises. Note that if we were dealing with algebra instead of geometry, then an expression of such as AB usually would denote the product AB. In that case, Grassmann's suggestion of AB violates one of the sacrosanct laws of arithmetic that two quantities multiplied together produce the same result irrespective of the order in which the quantities are taken. Grassman faced up squarely to this disturbing possibility and invented few consistent algebra known as exterior algebra that allowed for several processes of multiplication and at the same time could handle geometry in any number of dimensions. By the 1860s, and dimensional geometry was spreading like mushrooms after a rainstorm. Not only had Riemann's seminal lecture established spaces of any curvature and of arbitrary numbers of dimensions as a fundamental area of research, but other mathematicians such as Arthur Cayley and James Sylvester in England and Ludwig Scauli in Switzerland were adding their original contributions to the field. Mathematicians started to feel that they were being freed from the restrictions that for centuries had tied mathematics only to the concepts of space and number. Those ties had historically been taken so seriously that even as late as the 18th century, the prolific Swiss mathematician Leonhard Euler (1707 until 83) expressed his views that mathematics in general is the science of quantity, or the science that investigates the mean of measuring quantity. It was only in the 19th century that the winds of change started to blow. First, the introduction of abstract geometric spaces and of the notion of infinity in both geometry and the theory of sets had brought the meaning of quantity and of measurement beyond recognition. Second, the rapidly multiplying studies of mathematical abstractions helped to distance mathematics even further from physical reality, while breathing life and existence into the abstractions themselves. 1854, 1845 until 1918, the creator of set theory characterized the newly found spirit of freedom of mathematics by the following declaration of independence. Mathematics in its development entirely free and is only bound in the self-evident respect that its concepts must both be consistent with each other and also stand in exact relationships ordered by definitions to those concepts which have previously been introduced and are already at hand, and its abilities to which algebraic Richard Dedekind 1831 until 1916, 86 years later. I consider the number concept entirely independent of the notions or intuitions of space and time. Numbers are free creations of the human mind. That is both Cantor and Dedekind view mathematics as an abstract, conceptual investigation constrained only by the requirement of consistency and with no obligation whatsoever toward either calculation of the language or physical entirely. As Cantor has summarized it, the essence of mathematics lies entirely in its freedom. By the end of the 19th century, most mathematicians accepted Cantor's and Dedekind's views on the freedom of mathematics. The objective of mathematics changed from being the search for truths about nature to the construction of abstract structures, system of axioms, and the pursuit of all the logical consequences of those axioms. One might have thought that this would put an end to the all agonizing over the question of whether mathematics was discovered or invented. If mathematics was nothing more than a game, albeit a complex one, played with arbitrarily invented rules, then clearly there was no point in believing in the reality of mathematical concepts. Was there surpassingly the breaking away from physical reality infused some mathematicians with precisely the opposite sentiment. Rather than concluding that mathematics was a human invention, they returned to the original Platonic notion of mathematics as an independent world of truths whose existence was as real as that of the physical universe. The attempts to connect mathematics with physics were treated by these non-Platonists as dabbling in applied mathematics as opposed to the pure mathematics that was supposed to be indifferent to anything physical. Here is how the French mathematician Charles Hermite, 1822 until 1901, put it in a letter written to the Dutch mathematician Thomas Johannes Tilges, 1856 until 1940, until 94. On May 13, 1894. My dear friend, he wrote, I feel very happy to find you inclined to transform yourself into a naturalist to observe the phenomenon of the arithmetical world. Your doctrine is the same as mine. I believe that numbers and the functions of analysis are not arbitrary products of our mind. I think that they exist outside of us with the same necessary characteristics as the things of objective reality, and that we can encounter them or discover them and study them just as the physicists, the chemists, and the zoologists. The Danish mathematician G.H. Hardy himself, a practitioner of pure mathematics, was one of the most outspoken modern Platonists. In an eloquent address to the British Association for the Advancement of Science on September 7, 1922, he pronounced, Mathematicians have constructed a very large number of different systems of geometry, Euclidean, of non-Euclidean, of 1, 2, 3, or any number of dimensions. All these systems are of complete and equal validity. They embody the results of mathematicians' observations of the reality, a reality far more intense and far more rigid than the obvious and knowledge reality of physics. The function of a mathematician, then, is simply to observe the facts about his own heart and intricate system of reality, that astonishingly beautiful complex of logical relations, which forms the subject matter of his science, as if he were an explorer looking at the distant range of mountains, and to record the results of his observations in a series of maps, each of which is a branch of pure mathematics. Clearly, even with the contemporary evidence pointing to the arbitrary nature of mathematics, the die-hard Platonists were not about to lay down their arms. By the contrary, they found the opportunity to delve into in hardest words the reality even more existing than to continue to explore the ties of physical reality is irrespective, however, of the opinions of the metaphysical reality of mathematics. One thing was becoming obvious, even with the seeming unbridled freedom of mathematics. One constraint remained unchanging and unshakable, that of logical consistency. Mathematicians and philosophers were becoming more aware than ever that the umbilical cord between mathematics and logic could not be cut. This gave birth to another idea: could all of mathematics be built on a single logical foundation? And if it could, was the secret of its effectiveness? Or conversely, could mathematical methods be used in the study of reasoning in general, in which case mathematics would become not just the language of nature, but also the language of human thought?